Okay, folks, this is Raj. This video I'm going to show the desired output of the AUV assignment 6. So all my controller is in AUV.m. Not like the S function has all the dynamics as well as all the forces and moments, and it takes. So if you see this simulation here, so this is the AUVS function. This is the single file I'm using. I'm not using forces and moments separately. So it takes basically 6 uh, forces, and let me make everything 0 except, so I'm putting this just to counter the gravity force so that the vehicle doesn't go down. So I'm using 101 there. So if you keep force to be 101 Newton, I think the vehicle will stay there. So if your vehicle, if you put 101 and your vehicle is going down, there is something wrong. So let's get started and see how it looks. So that's my AUV, which looks like quadcopter. Yours should look better than mine. And so let's see. I can plug this in. I can zoom out. So just in case. So let's see. If you give a little bit of force, so this is complicated. If you see initial small force, the vehicle initial small force in forward direction of point 1, you will see that it starts increasing north. Your height starts increasing, and a little bit, not much, but you will see your theta is kind of increasing here. Of course, your forward velocity u is increasing because I gave a forward force, and then you'll see that it reaches some value and then it kind of tumbles. That's because of the Coriolis forces, and then it will do a tumble in one direction and then tumble in the other direction. So symmetrical, and that's because of the drag forces. The drag kind of changes sign when so kind of drops down. So you should see these trajectories. So theta basically goes up and down to 360 degree. So that's one behavior when you increase forward force. So this will be a challenging control problem. So now let's see if I make this again 0 and rerun it. Right, so if we rerun it, let's give some 0.1 of yaw rate. So I'm giving yaw rate. It should rotate along the axis. So you will see that psi has started increasing. So it's slowly moving, and this is degrees here, so moving pretty slowly. You'll see R also kind of tapers down. So that's good thing that the drag, so it reaches an equilibrium point. So when you give if this is not there, if the drag is not there, it will spin very fast. So you'll see that R reaches a stable value, and then if psi it's rotating very slowly. I don't see it, but I can see it in the graph that heading is increasing 4 degrees. So you can in fact increase it and see what happens. You can make it like 1 radians. So you'll see again this yaw thing. It reaches an equilibrium point again, yaw rate R, which is the yaw rate, and your vehicle is now moving slowly. You will see the forward phase. So it's pretty stable in yaw direction. So in yaw direction, it reaches an equilibrium point. But when you give forward force or anything other than yaw, it reaches an equilibrium point and then the tumbling starts. You see that, right? It's pretty amazing to see the R reaches equilibrium and then your heading is increasing. So it's moving very slowly because of the drag. Otherwise, 1 Newton meter of torque is a very large torque, and if any other vehicle was there, if it is not in the water, it will move really fast. Like, it will go unstable by now. You'll see that because it has reached equilibrium point here on R, it's moving slowly. So now let's see if I can, let's make it 0 again. So pretty stable behavior in yaw rate. But if you give, let's say, some sideways force to it, so it will try to reach equilibrium, but because of the cross coupling, it will. So see now that because I have given in Fy direction, force in Fy direction, you're seeing some movement in east, but you're also seeing some movement in roll rate. That means your phi is changing, means your roll angle is changing. So it kind of reaches the P. There will be a point where it will become it will start oscillating. So this side and then the opposite side. So every other direction other than yaw is kind of it depicts an oscillating behavior, a very symmetrical behavior. It goes in one direction, then comes back in another direction. So we can also see what will be. Generally, UUVs we won't be using roll and pitch. But I can show you what happens when we change 0.1 of roll. So there is no drag in roll and yaw, so you will see it will spin, it will go berserk. But yeah, so you'll see keep increasing. This time it's not changing the direction because there is no drag term. The drag term in phi and theta is 0. So you'll see. Yeah. Okay, so that's how it should look like. Hopefully you'll be able to submit a similar video. Thank you.